Now we are going to discuss the assessment of classification models where the target variable is categorical and prediction models where the target variable is numerical. Performance measures used in classification and prediction models are different, so that's why we're going to discuss them right now. So this is the idea of the performance measure for classification models. We did some of them, but we're going to now just talk about the overall idea. The performance measures for classification models can be computed from something really nice. We call it confusion matrix. Confusion matrix is nothing but a table that summarizes classification outcomes obtained from the validation dataset. And this example that we have, this table, is for a binary classification problem, so 0, 1. Assume that the target class, which is called the success class, is a class 1, and the non-target class is class 0. So we have the target class, which is the success, is 1, and the non-target class is 0. So in this confusion matrix, we can see only two correct classifications possible: the true positives and the true negatives. The true positives, these are the actual class number 1, class number 0. This is the predicted class 1, predicted class 0. So the 1 is the positive, right? So the 1 is the positive. The 1 is the positive for the prediction. So the 1 is the positive. The 0 is the negative. So here, the predicted class 1, it's the positive, and it's matching the actual class. So it's a true positive because we predicted the class truly. I mean, it's a true. So that's why it's a true positive. Positive because it's 1 for the predicted, and this is true because we predicted the class correctly. Class 1 observation that is correctly classified by the model. The true negative, on the other hand, here, in a class 0 observation that is correctly classified by the model. So this is negative because it's 0, and it's truly classified by the model, right? We have false positive, in a class 0 observation that is incorrectly classified as a class 1 observation by the model, and we have false negative, is a class 1 observation that is incorrectly classified as a class 0 observation by the model. So we have false positive. It's positive because 1, and it's false. We said 1, but this is false. The model said 1, right? But this is false. It should be 0, right? It should be 0. Here, the model said 0, and this is false. The model said 0, negative, and this is false. It should be 1, right? So this is the way that we try to memorize this table. We discussed some of these measures. Misclassification, accuracy, sensitivity, and specificity are among the most common performance measures for classification models. So these are for classification models like logistic regression, naive Bayes, KNN, and so on. What is the misclassification rate? We call it the error rate. It's the overall proportion of the observations that are misclassified. So the misclassification rate measures how often the predictive model makes an incorrect prediction. It's computed using this formula. You just plug in the numbers here. If you have the confusion matrix, then you can plug in the numbers, so it's easy. What is the accuracy rate? The accuracy rate is just 1 minus the misclassification rate. It's the opposite way around, right? It's the overall proportion of the observations that are classified correctly. It measures how often the predictive model makes a correct prediction, right? And we can use this formula. Next, we're going to talk about sensitivity and precision and specificity. Sensitivity, we call it sometimes recall, which is the proportion target class cases, the observations that are classified correctly, is the proportion of target classes. It's the proportion of the target classes that are classified correctly. This is important. Is the proportion of the target classes. So to better understand the importance of the sensitivity, let's look at an example of a model. For predicting breast cancer among a group of patients, a predictive model with 100% sensitivity would correctly identify all patients who have cancer, which is perfect. A model with 60% sensitivity would correctly identify only 60% of the patients with cancer. Cancer is a true positive. But have the remaining 40% with cancer undetected and untreated, which is the false negatives. So developing a predictive model with a high sensitivity is clearly important to help identifying patients with life-threatening but treatable disease. And that's why we need to think about sensitivity as well. And we did this in our default unknowns example. Precision is, we call it positive predictive value. It's the proportion of the predictive target class cases that actually belong to the target class. What is the difference between sensitivity and precision is the denominator is based on the predicted class 1 cases, not the actual class cases. Predicted class 1, not the actual class 1. So that's why I look at the denominator. True positive, false positive. In the sensitivity, we have true positive, false negative. So if you go back again, considering the breast cancer example, so the sensitivity rate measures the proportion of the patients with the cancer who test positive. The precision rate measures the proportion of the patients with a positive test who in fact have the cancer. A predictive model with a low precision rate would unnecessarily subject many patients who are cancer-free to undergo further medical tests and treatments. So you are including people we don't need. So these are important measures. And the third one, and we discussed this earlier, which is specificity, is the proportion of the non-target class cases that are classified correctly. And using this formula, again, going back to the breast cancer problem, a predictive model with 100% specificity would correctly identify all patients without the cancer. A model with 75% specificity would correctly identify 70% of the customers or patients as cancer-free true negatives. But we have 25% remaining of patients who are cancer-free are classified by the model as having the cancer. So these 25% of the patients may be subjected to further medical tests, but this is unnecessarily, right? So let's say these measures collectively represent the performance of the classification model. When the misclassification costs are symmetric for both target and non-target cases, the misclassification rate and accuracy rate are good indicators of good performance. However, emphasis may be placed on sensitivity or specificity measures when the misclassification costs are asymmetric or when the proportion of the target class observations is very small. So it depends on the data. If you have symmetric or asymmetric, we use these or those. Just if you go back to the example we did in the logistic regression, we had calculated the accuracy rate and we got very high accuracy rate. Well, this is not accurate. This is misleading because we got high overall accuracy rate, and this is a result of classifying the large number of non-defaulter borrowers correctly. And we got high accuracy rate because we have low target classes. That's why in that example we focus on the specificity and sensitivity, and these two measures, making the balance between these two measures is important in these cases because we have asymmetric data set. We have very low numbers of the defaulters, if you remember. That's why we did not focus on the accuracy rate. So in practice, in order to assess the performance of the classification model, we often compare the model with a baseline or benchmark. A common baseline approach is to compare the accuracy rate of the model with that of naive rule, where all cases are classified into the most predominant class. In the context of the binary choice models presented earlier, we computed the probability that a borrower will default on loan, which was the class 1, or no, the class 0, he's not going to default class 0. If the predicted probability value was greater than or equal to half, 0.5, we classified the new borrower, or the borrower is belonging to class 1, that he's going to default, and 0 otherwise. In other words, we used a default cut-off value of 0.5. Classification techniques in all supervised data mining follow similar process where the class membership is determined by comparing the predicted probability of the target class to a predetermined cut-off value, the minimum required probability of belonging to the target class. And as we discussed, with imbalanced data, the analyst may choose to increase or decrease the cutoff value, increasing and decreasing the cutoff value y to classify fewer or more observations into the target class due to asymmetric misclassification costs or uneven class distributions. As a result, the choice of the cutoff value can influence the confusion matrix and the resulting performance measure. So we have an impact on this. And we will be discussing the impact of the cutoff value on the performance measures of the classification model. Look at this example. We can see the target class, the actual class first, some observations, actual class, the target class probability, and predicted target class by different cutoff values. If the cutoff value is 0.15, so if it's greater than this, put 1 other than 0. For example, this one is 0.73, greater than 15%, 1. This one greater than 15%, 1. This number greater than 15%, 1. This number less than 15%, 0, and so on. If you increase that and compare the predicted target class with the actual class, and increase the cutoff values and see which one makes sense, which one is really the best cutoff value. by just quick comparison, you can look at the 25%, looks nice, it's predicting the cases well here, right? And we have here the rates, different rates, performance rates with different cutoff values. And look at the performance rates. Again, if you look at the sensitivity here, specificity here, the precision accuracy rate, misclassification rate, so it depends on the scenario, what you're looking for, the balance between all of these is good. And if you have asymmetry or symmetry data, this is the thing. If you have symmetry, we focus here. If we have asymmetry, we focus here. Yeah, but these are different. Look, we have different performance measures with different cutoff values. Now we can look at the charts. So we have charts because sometimes seeing things, graphical representations are informative to assess the predictive performance of the data mining techniques. We have popular performance charts. The first one, it's called cumulative lift chart. The second one, decile wise lift, and the third one, the ROC, we call it receiver operating characteristics. We call them by the short name, which is our ROC here. So the cumulative lift chart and some other resources called the cumulative gains chart, or maybe lift chart. The lift is a bit different, but this is the cumulative lift or the cumulative gain. So this shows what? The improvement that a predictive model provides over random selection in capturing the target class cases. It's allow us to determine the point at which the model's prediction become less useful. This one displays a cumulative lift chart for a classification model. The chart shows the number or percentages, but here we have the numbers of the target class cases gained by targeting a number of all cases or percentages. So the x-axis indicates the number of cases selected, and the y-axis represent the cumulative number of target classes, which is a class 1 cases. These are the ones that are that identified by the model. And the orange straight line or diagonal line represents the baseline model where observations are randomly selected without using any model. The slope of the diagonal line is the number of class 1 cases divided by the total number of cases, or it's the probability of a randomly selected case belonging to class 1. For instance, in this example, it shows 475, which is here, 475 of the 5,000 total cases belong to class 1. So the probability of a randomly selected case belonging to class 1, or the slope of the diagonal line, is about 0.095 if you divide these two numbers, 475 over 5,000. And this is important. Why? Because we need to look at the blue curve. The blue upper curve, we call it the lift curve. That represents the ability of the classification model to identify class 1 cases. Again, we're talking about class 1. This is the target cases that we're looking for. The people who are gonna default, the ones who have breast cancers, the buyers, the focus, the target cases. To construct the lift curve, the observations in the validation datasets are sorted in descending order. This is important, based on their predicted probability of belonging to the class of the target class, which is class 1. So we're gonna do the prediction, a probability, then we classify or sort them descending order from the biggest, the highest to the lowest, right? And for instance, if you select the top 2,000, observations with the highest probability, with the highest predicted probability of belonging to class 1, you will capture, this is important, you will capture 465 out of the total, which is, we said 475 classes. We said we have 475 classes, cases 1. So if you select the top 2,000 observations with the highest predicted probability of belonging to class 1, you will capture 465 out of the 475 class 1 cases. But if you randomly selected 2,000 observations, you will likely to capture only 190 class 1 cases. Randomly. If you do this randomly, the random selection is gonna maybe give you about 190 class 1 cases. But using the predictive modeling, you may capture 465 belongs to class 1. The ratio between these two numbers, if you divide this number over this number, this one we call it the lift, which is the ratio of the number of the class 1 cases captured by the model to the number captured by random selection. We call it the lift. And here, the cumulative lift chart shows that when you select 2000 observations, the model provides a lift of what? Divide this over this, what we get? We get about 2.5. This means among the top 2000 observations selected by the model, you are able to capture about 2.5 times as many class 1 cases as compared to the 2000 observations selected randomly, which is good. So the cumulative lift chart shows how well a predictive model can capture the target class cases compared to the random selection. And what we care about, what we're looking for, we are looking for a high lift number. A high lift number is desirable in most applications, ranging from marketing to fraud detection, as it means that we are able to capture a large proportion of the target class cases by only focusing on a smaller proportion of the cases with a high predicted probability. There's no need to go further. Just focus on the top 1,000 or 2,000 of the cases. They will be capturing what you're looking for. So the lift curve usually is above the baseline. If it's above, we have a good indicator. We have a good predictive performance of the model. Further above the baseline, the lift curve lies, the better the model's ability to correctly identify target class cases. We don't want this guy to be close. We want this guy to be further away from the baseline. Another chart which is similar to the previous one, which is the decile-wise lift. This gives the same information as the cumulative lift chart, but represents the information usually in 10 equally sized intervals, so every 10% of the observations. So it's usually presented by a bar chart where the y-axis represents the ratio of the target class cases identified by the model to the identified through random selection. So look at this one. This one shows the lift for the first 10% of the observations is about 7.1, which means that the top 10% of the observations selected by the model contains 7.1 times as many class 1 cases as the 10% of the observations that are randomly selected. It also shows us, to determine the point at which the model's predictions becomes less useful. For example, look at this. After the second decile, the lift values drop below 1. It becomes below 1. Suggesting that the model will capture fewer target cases than random selection in the subsequent deciles. So in this case, we want to focus only on the first 20% of the observations that have the highest predicted probability of belonging to the target class. If our goal was, remember, if your goal was to capture the target class cases, which is normally the case. The third and the final one, which is the ROC curve, this shows the sensitivity and specificity measures across all cutoff values. Let me look at that. And how accurately the model is able to classify both target and non-target cases overall. So what is the x-axis? The x-axis is equal to 1 minus specificity, and it ranges from 0 to 100, right? To 100%. 100%, the zero, by the way, look, the 0 means 1 minus specificity, which is classifying 100% of the non-target class cases correctly. But the value of 1 means classifying 0% of the non-target class cases correctly, because it's 1 minus specificity, right? And the y-axis is equal to sensitivity. It ranges from 0 to 100% again. 0 classifying 0% of the target class cases correctly, 1 classifying 100% of the target class cases correctly. So what is the perfect point? The perfect point simply is going to be the one in the corner. We have high sensitivity here, we have high specificity here, right? Which is big. We would like this guy to touch 0,1. If it touches 0,1, then we're good. That we are able to correctly classify 100% of both the target and non-target. But this is not, we will never have this, right? But the case is, these are with different cutoff values, by the way. So this point, you have to look at what the cut value that gives you this in the corner, right? And again, the ROC curve, along with the orange diagonal line, that represents the baseline model that randomly assigns the observation to the two classes based on the prior probability of the target class cases. So a good predictive model, as we said, that have ROC curve that lies above this baseline, and the greater the area between these two, the better the model is. And the overall performance of the model can be assessed using the area under the curve. The area under the curve, AUC. We have bigger area. And the area ranges between 0 and 1. 0 is the worst model, 1 is the perfect model. And the diagonal line has AUC a value about 0.5. And R does this for us. If you have like AUC 0.9, it's very high. Like here, it's very high. This is good. This is perfect, right?